materials such as graphene. And then later I moved to electrical optical properties and applications. In this case, what we talk about later applications will make more sense to you. And I see this summer school largely as a tutorial. So what I'm going to do, I will try to keep it relatively simple. Don't hesitate to interrupt me if you have any questions. And please take notes and try to understand what I'm talking about here. I won't talk much about our research, but I will introduce a little bit what we do. Before going to carbon nanotubes, let me also mention a few things here. At Drexel University, I coordinate activities in the nanotechnology field as the director of the Drexel Nanotechnology Institute. And this is a kind of a coordination center university where we have more than 30 faculty doing research in nanotechnology field. We have probably at least 100 of students involved one or another way in nanotech research. And we work with companies. We also have very nice centralized research facilities. We always look for good PhD students and postdoctoral researchers. If anyone is interested, if anyone gets excited, you're always welcome to Drexel University. And some of the work that I'm going to describe today will be related to making transparent conducting films of carbon nanotubes. And I understand also that a number of you work on liquid crystal applications. So one of the goals of these films is to replace indium tin oxide, replace ITO in, for example, liquid crystal display applications. Of course, there are many, many other applications of carbon nanotubes here. But my research activities span a broader field than nanotubes. My students work on carbon nanotubes, diamond nanomaterials, porous carbons, and testing characterization of a variety of materials. Mainly carbon, and I'm acting as a co-editor of Carbon Journal, but also variety of other materials at the nanoscale for electronic applications, functional applications, and others here. But again, as I mentioned today and tomorrow, I'm going to talk very little about our own research. It will be largely a tutorial giving you an opportunity to learn more about carbon. Okay, why carbon? Why carbon is important here? Because like water, fire, air, carbon is the critical element for us. We all are built of carbon. We represent the carbon world. But as we're moving to the era of nanotechnology, carbon-based materials become more and more important in a variety of applications. And I like this centerfold and a cover from Business Week, published already a couple of years ago. It was on general subject, commercialization of nanotechnology. But what I found very symbolic in this article, talking about nanotech in general, the author illustrated it with 3 carbon materials. And I don't think my laser pointer works well enough for you to see it. Graphite, diamond, and carbon nanotubes. And I think this shows you the role that carbon plays in modern nanotechnology. And this is one of the reasons why about 5,000 papers are published every year on carbon nanotubes alone, plus many, many others on other materials. Right. So, what I'm going to do is very quickly run through some of the basics which you may recall from high school chemistry, bonding in carbon materials, going into structure of carbon nanotubes, going into electrical properties, and then move to applications here. Why is this important? Because as you understand, all properties of materials are controlled by their bonding. And in carbon, we may have so-known sp, sp2, and sp3 hybridization of orbitals, which lead to sigma bonds. Those are strong bonds in diamond that make diamond transparent, very hard, girl's best friend, or wide bandgap semiconductor if doped, or an insulator if not doped, depending from under what angle you look at this material here. But you can also form pi bonds from this side wall overlap of pi orbitals. And these are electrons which are mobile. These are electrons which are responsible for conductivity of graphite, graphene, and carbon nanotubes. Moreover, which lead to ballistic conductivity, and we will talk about it later, what it means, of graphene and carbon nanotubes, enabling use of these materials in transparent conducting fields. All the materials we're talking about today are based on double bonded carbon, as chemists say, or sp2 bonded carbon materials, which is a bond which is intermediate between sp and sp3 bonding here. So largely those are graphene based structures here. And have you heard the term graphene? What is the difference between graphite and graphene? Graphene is just a single layer of graphite. Very, very simple. Why is it flat? Because sp2 sigma orbitals are all in one plane, forming a 120-degree angle between the planes, and this is how graphene layer looks like. If you stack a number of layers of graphene, you will get graphite. If you roll a layer of graphene in a tube, you will get carbon in a tube. But, as probably many of you know, graphene is gaining importance now as a material by itself. Moreover, it's probably the hottest member of carbon materials family. One of the reasons is it has been relatively recently discovered and shown that it can exist as a single layer or a small number layer of material with a number of wonderful properties. So I'm going also to give some information about graphene today for comparison with carbon nanotubes here. So this is a graphene which is right in the middle, forming a two-dimensional carbon structure. And we can go from it to graphite, which we won't talk about today, and to carbon nanotubes, which we will discuss a lot. And graphene has very good electrical conductivity in plane, but in graphite will be the same. Very high conductivity in plane, very low conductivity between the planes, because you have van der Waals bonds, very weak interaction, and low conductivity. Very similar way will be in carbon nanotubes. You will have very high conductivity along the tube, but low conductivity relatively between tubes here. And graphene has also interesting properties such as ballistic conduction. So basically conduction and very fast transport of electrons over relatively large lengths with little resistance here. So graphene itself is very simple network of carbon layers. What you see here is an image of graphene sheets, and the thinner one are probably monolayer of graphite here. So from 1 to 10 layer we call it graphene, with monolayer graphene being a single layer, and above 10 layers we pretty much get graphite fields. I think it's very simple and fairly clear. But for a long time it was believed that no single layer of material can exist unsupported. And that's why this was such a surprise when Gaiman and Marcello, two scientists from England, published from University of Manchester, published a paper showing that graphene, single layer graphene, has very attractive electronic properties. But what is also interesting is that this type of a 3D warping leads to gain elastic energy, suppressing thermal vibration. And this was the reason why many famous scientists, including say Landau, believe that it's impossible to make single layers of atoms of any materials exist independently here. So this predicts collapse of these two-dimensional films, making graphene stable. However, still, thermal vibrations can lead to rolling graphene sheet in this way into a tube, or it can lead to bending graphene sheet and formation of van der Waals forces between two layers. As a result, you will get, say, double layer graphite, double layer graphene with like a half a nanotube layer here, as it is shown in these images here. So this is graphene sheet bonded like that here. So what I want you to understand from this, that there is really a continuum within the range of carbon nanomaterials. So graphene, graphite, carbon nanotubes, and very large variety of nanotubes we are going to talk about today are all related. What is important for us is to learn how to build these materials, how really design structures at the nanoscale with the properties that we need for specific applications. And this is what scientists do in nanotechnology. So with the same layer of graphene, this chicken wire of carbon atoms, you can build fullerenes by incorporating pentagons and pentagonal defense, which are spherical soccer ball-shaped carbon molecules. You can form carbon nanotubes by making seamless cylinders or scrolls of graphene, or you can stack these layers forming graphite, which we all use in pencil leads. Moreover, does anyone use pencil to take notes of my lecture? Well, I think a couple of people here. Do you know that you produce graphene when you do it? Because you basically take thin layers of graphite and transfer them on paper. And this is how initial experiments, for example, Game and Novoselov, were done, by pretty much peeling off thin layers of graphene from the surface of larger crystals here. So you generate graphene and do some nanotech work when I use a pencil. So this is the oldest way to generate carbon nanostructures, probably here. Now, what is also important to mention that when you bend graphite layer, you actually move towards sp3 bonding in carbon. Can you explain to me why? What does happen if I take carbon layer and scroll it like this bend? What happens? I change the bond angle. So the angle between carbon bonds becomes not the same as it was in a single layer of graphite. With, as a result, properties change. For example, you will see that band gap in carbon nanotubes depends on the nanotube diameter. Because as we move to smaller diameters of fullerenes or carbon nanotubes, we get them closer and closer to sp3 bonding. With the form bond angles to such an extent, they get closer to bond angle in diamond and further away from graphite. So in the smallest number of fullerenes family, for example, SWNT, you see the bond angle is much, much closer to diamond, sp3 bonded carbon, than to graphite. Most of carbon nanotubes lay in this range. So this determines some differences in properties between carbon nanotubes and graphene and graphite here. Now, what is a carbon nanotubes? Well, there are different ways to explain it. One I mentioned to you. Just take a graphene sheet, scroll it, make a seamless cylinder, and you get a carbon nanotube. There is another way to present carbon nanotubes. Consider it to be an extended fullerene. What you see here is a C60, soccer ball-shaped fullerene molecule discovered by Crota and Small and their team in 1985. When I add one layer of carbon, here, forming a C70 molecule, I will elongated. I'll add second layer, I can add third layer and fourth layer, and ultimately I will get a nanotube. So this is an extended fullerene molecule. And nanotubes that have a single layer of carbon atoms in the wall we call single wall carbon nanotubes. Or you will often see this abbreviation, SWNT. Accordingly, if you have two layers, you will get double wall carbon nanotubes, triple wall carbon nanotubes, or multi-wall carbon nanotubes, which all have very different properties here. So, nanotubes were discovered by Ijima in 1991. However, if you look in all the literature, there have been transmission electron microscope images of carbon nanotubes shown as early as in 1959 by some Russian scientists, multiple carbon nanotubes. And there were later few other mentioning of tubes in literature in Japan and elsewhere. But the reason Ijima's discovery attracted attention was that fullerenes were discovered in 1985, fairly short time before that, and made a big splash. Scientists realized that it is possible to build complex three-dimensional structure of carbon at the nanoscale. And things that did not really attract anyone's attention earlier became important, and that's why this rediscovery of carbon nanotubes by Ijima was so timely and pretty much caused revolution in science, leading to very fast development of nanotechnology. And very quickly after that, large quantities of monotubal connected single-wall nanotubes were discovered, and further progress has been going on. Now, as I mentioned to you before, about 5,000 papers on carbon nanotubes are published every year. So you can imagine how many scientists around the world work on carbon nanotube materials here. And I think a number of graphene papers exceeded 1,000 last year as well. Now, just to give an idea to those of you who are not into nanoscience and carbon nanomaterials, how small they are. We just talked that carbon nanotubes is an extended fullerene here. So if you compare fullerene with a soccer ball, the size ratio is the same as a soccer ball to our planet Earth. So those are really very small things. The diameter of a C60 fullerene molecule is 0.66 nanometers. Question?
Yes, I wonder if you can explain a little bit about the mechanism of control the growth of this single wall, double wall, multiple wall. What's the mechanism of that?
Good question. Let me see if I have actually, I removed the slides on the synthesis of carbon nanotubes. But usually there are two ways, or two major ways to make carbon nanomaterials. Typically, these tubes grow through catalytic growth. So you have a metal catalyst particle, carbon from the environment, for example, carbon monoxide, or any other environment, get dissolved in this particle on the substrate and get crystallized, forming nanotube walls here. And if it goes this way, grows, you usually get a multi-wall carbon nanotubes with the metal particles at the tip growing on a substrate or in environment. However, there is some other different mechanism. So, when you dissolve carbon, then abruptly, because of such instability, when carbon crystallizes on the surface, it does not crystallize as a graphene layer. And reason for this is fairly unusual. When you look at graphite, if you have single, like a hexagon of graphite, it's energetically very, very expensive, because you have dangling bonds and very high energy atoms which are at the edges here, compared to, say, an atom which would be in the middle, covered here. So what happens? Graphite forming somewhere on the surface would form rings, linear chains, rather than hexagons. So C60 will be energetically preferred form of carbon for number of atom of 60. If you go to roughly 1,000 atoms, for example, nanodiamond will be lowest free energy state of carbon. But if you talk about small clusters like a 10, 20 atoms less, carbon rings and chains are the most preferred one. So what happens? You have a formation of a ring like that, and then addition of new atoms happen, and this ring grows ultimately in a single wall carbon nanotubes. Here. So this is how usually different mechanisms happen. There are some related mechanisms, for example, solid-state synthesis of carbon nanotubes from silicon carbide, where you again form rings, but not in a liquid catalyst droplet, but on the surface of silicon carbide. And the mechanism, many of the mechanisms are still being discussed in literature, and there is still a lot of controversy about details of how it happens. But what is important for you to know now is that there are ways to grow single wall nanotubes, double wall nanotubes, triple wall nanotubes, multi-wall nanotubes with relatively high selectivity. What we still don't know how to do is how to grow just metallic carbon nanotubes or just semiconductor nanotubes. Moreover, not just semiconductor nanotubes, by nanotubes with certain chirality and with a specific band gap. And this would be the dream, of course, of all engineers working on electronic application of these materials here. But, so hope it answered your question at least partially. Here. Now, carbon nanotubes are important. I won't repeat it here. And actually, this is a slide that I probably needed to show to explain this. One thing that is very important, please pay attention to this. When you look at the sheet of graphene, you will see that it may have edges which look like that, and we call them zigzag edge. And it's clear why. Or you can cut it in another direction and form something that looks somewhat like armchair. And it's called armchair edge. And I can roll this graphene sheet in different ways to form either armchair nanotubes, which will have an armchair edge in the cut, or zigzag carbon nanotubes, or anything else will be called chiral nanotubes. And all of them interesting, all of them have practical applications, as you will see in the future here. So this is how it's happening here. This is, for example, an example of formation of nanotubes. Which what kind of nanotube will it be? Can you tell me? Armchair, zigzag, or a chiral? Armchair, absolutely correct. Why armchair? Because at this edge you will see you have the armchair structure along the edge of tube here. If I roll it this way, tube, I would get a zigzag tube, because this is a zigzag edge, this is the armchair edge. So, different ways to cut it, different ways to make carbon nanotubes, depending which way I scroll graphene sheet. So, it is fairly simple. Three types, major types of single wall nanotubes, which have different properties, different conductivities. Particularly, these tubes may also have very interesting optical application, because any chiral structure will lead to polarization of light, maybe, or very interesting optical application. What we still don't know how to do, or just learning how to do, it's done at very small quantities in lab scale, is how to separate structure. But it has been shown that you can make left-handed, right-handed chiral structure separated, and also separate semiconductor nanotubes from conducting tubes and separate them by diameters here. It is still one of the major issues for those of you who are in the field here. And as you also know, this is not that unusual. This is an atomic model of the nanotubes, which we built using, I think, Material Studio software. And this is two images of similar structures that I took myself with a camera at the microscopic scale. And you see one of them chiral, one not. And exactly as you buy corn, and you will see a different type of structures, very similar way. In any single sample of single wall nanotubes that you get from any producer in the world, you will get a mixture of chiral, zigzag, and armchair nanotubes nowadays. Here. Now, couple of important things about carbon nanotubes. Every single nanotube can be characterized by simple combination of two numbers, which are called Hamada indices. How do we do this? We take any carbon atom on the surface and select it at a zero coordinate point here. You have two lattice vectors, A1 and A2, going, as you see, along zigzag directions. And you use those vectors as your coordinate axis here. So if I go 3 points, this direction, 3 steps, 3 lattice periods, I will get a 3, 0 carbon nanotube. Which I go 2 steps this direction and 2 following the other direction in the lattice, I will get 2 carbon nanotube. If I go this way, what will be Hamada indices of this point? 0, 3. Is there a difference between 3, 0 and 0, 3 nanotube? No. There is no difference because I can take any of 6 zigzag directions in 2D lattice of graphene. They all are equal. There is absolutely no difference here. And accordingly, this tube will be 4, 4. This tube will be 5, 2 if I go this direction. So this is very important. And again, think about it. I would like every one of you be able to understand here. Also, when you look, someone tells you, I have 5 nanotubes. You should be able to immediately tell that this tube will be armchair, because if N and M are the same, 2, 2, 4, 4, 5, 5, this is an armchair nanotubes. If one of Hamada indices is equal to 0, this is a zigzag nanotube. If they're non-zero and not equal to each other, those are all chiral nanotubes. Is this clear? Very good here. Okay, let's make it more complicated here. This is a space with all the points here marked. What is important? Hamada indices determine everything about carbon nanotubes. If I know Hamada indices, I can immediately tell whether this tube will be metallic or semiconducting. So tubes that are armchair are all metallic. Tubes which have N minus M difference divisible by 3 will be metallic. All other will be semiconducting. If I know N and M value, I can calculate nanotube diameter. So pretty much I can tell all what I need about nanotubes just from these 2 indices. So it's very important to understand it here. Now, can someone tell me here, I would like to have a nanotube 3.51. Place it here, basically selecting this point between 3.1 and 4.1 tube here. Can I do it? We have 3 nanotube experts in the room as far as I remember. So can I have a 3.51 nanotube? Yes or no? There is no grading for these things here. So if you give a wrong answer, that's okay here. What do you think? No, why not?
Because it will be some another excess. Because it will make some another excess.
I'm not sure I understand why. Well, if I can select any point on the plane, there is a carbon atom here. Why can it be 3.52? Can anyone tell me? The correct answer is no. So why not? Reason is simple here. If I scroll it, starting from that point, I will not be able to get basically a seamless cut on the nanotube here. So it won't coincide. When I take the sheet and bend it like this here, you cannot have half of a bond connected here. So you really need to go to, if you start your coordinate system here, you really need to roll it the way that you close and you have whole hexagons everywhere here in the lattice. So you cannot cut it. So Hamada indices are always whole numbers. 1, 2, 3, 4, 5, and so forth. And can you also tell me something? Can I have a nanotube which have Hamada indices, single wall tubes, 1,000 and 1,000? I want to have a very large nanotube, or a million. I want to have a single wall nanotube which will be of this dimension, 1 inch in diameter. Can I do this? Well, you're young scientists and engineers. Many of you are PhD students. This is a challenge. Can you deliver a nanotube like that? What will happen if I have a large nanotube, single wall tube? Louder.
It won't be stable.
It won't be stable. Why?
Because of thermal fluctuation.
Right. Thermal fluctuation will lead to eventually sides of the tube touching each other. What will happen at that moment? Van der Waals bonds will form between two graphene sheets, and this structure will become stable. So, tubes, single wall tubes larger than 6 nanometer in diameter will collapse, transform into carbon ribbons. Here. So, they cannot be larger than 6 nanometers, and the smallest diameter of a tube found was 4 angstroms, 0.4 nanometer. But again, it was not a single tube which is independent. It was a single tube inside a multiwalled nanotube constraint here. So typically tubes are from 0.6 to 3 nanometers that you find in single wall nanotube samples here. Okay, I'm not going to spend much more time on these structures. I hope you understand how indexing is done and can practice yourself at home. Determining Hamada indices for any point on this scale here. For example, this one will be 6, 3. And if you go on the other axis, you will end up with exactly the same index, and it will be the same here. Now, tell me something. Will 6-3 tube be zigzag, armchair, or a chiral tube? Louder. Zigzag, 6-3. Does everyone agree? I take it like this, cut the plane, and roll it this way. Will I get a zigzag tube? No, I will get a chiral tube. Zigzag must be along this direction or along this direction, and armchairs will be this. If I take it this way and scroll it this way, this will be the cut. This will be an armchair nanotube here. So there is something else useful to know, which we call is a chiral angle of carbon nanotubes. Because if we deal with chiral nanotubes, we need to know what the chirality is. And chiral angle is just an angle between the nearest wrapping direction. So unit cell vector direction and their wrapping direction. Basically, we determine where is the nearest zigzag orientation unit cell vector. This one, for example, or this one. Find the smallest one. This will be our chiral angle. And of course, the chiral angle, as everything else, can be calculated simply if you know Hamada indices. So again, by knowing Hamada indices, you can describe nanotube, and you can pretty much calculate after that all the properties. You can calculate the Raman spectrum of these carbon nanotubes, whatever you need here. And as you can see from scanning probe microscopy images, what I told you about structures, chirality, zigzag, and armchair orientation is a reality. You can image the structure. You can really see, for example, STM image of chiral carbon nanotube, and you can see images of armchair zigzag nanotubes in a similar way. So it exists. It is reality here. However, of course, the story does not end here. What is very important? Very often, you take a paper, for example, scientists talk about health effect of carbon nanotubes, or someone else talks about effect of carbon nanotubes on conductivity of polymer, and you read, we bought carbon nanotube from Sigma Aldrich, added 1 gram of nanotubes or 1 milligram of carbon nanotube to the mixture, and have done this study. If you read this at the beginning of the paper, my suggestion is you stop reading at that moment the paper and trash it. Because carbon nanotubes is not a single kind of material. Those are thousands really of nanostructures. As you already have seen, just single wall tubes will contain a large variety of armchair, zigzag, chiral tubes. But tubes can be also characterized by a number of layers, double wall, triple wall, multi-wall. They can also be scroll type structures, multi-wall nanotubes, or Russian doll structures, or Swiss roll structures, the scrolls if you want to come here. They can be open, then can be capped. They can be polygonized if they are larger tubes annealed at high temperatures. All these features, including presence of metal catalyst and kind of metal catalyst, will determine the properties here. So there is really no point to talk about any applications or any properties unless you know what kind of tubes to deal with. And before I finish, and I think it will be time for me to stop in a few minutes, I just wanted to show you some transmission electron micrographs. So this is a picture taken using transmission electron microscope of different tubes. This is a single wall tube, you see? This dark line is wall of a carbon nanotube, and this is a single tube here. And here you have 2 layers of carbon. So this will be a double wall carbon nanotube. These are taken by Haihu Yi, my former postdoc who works in Shanghai now for DuPont China here. But also very often, when you deal with small tubes, they will come not as single tubes. They will come in bundles. What is the reason nanotubes bundle together very easily? Any suggestions?
Like between graphene?
Right, like graphite. Van der Waals interactions between tubes at this very small distance. So you will see a bundle of carbon nanotubes, and here you can see actually nice hexagonal ordering within this bundle for tubes of the same diameter. And if you take lower magnification image using the scanning electron microscope, this is how a sample of single wall carbon nanotubes will look like. But what you see here are not single tubes. Those are bundles of single wall tubes. And material like that is usually called Bucky paper or carbon nanotube paper. and it's produced just by filtration and drying or deposition from a solution of cylindrical nanotubes after purification, after removal of amorphous carbon from samples here. So this is how the material look like. This will be conducting black colored paper. No more, not less. Here. And of course, you can add the layers. This is a TM image of a triple wall nanotube. 3 layers. And there will be about 10 layers in the wall here now. This will be a multi-walled carbon nanotube. And to make things even more complicated, what you can do, you can scroll tube in a kind of a conical scroll. As a result, as you see like in this here, you will have continuously edges. It will be cylindric over length here. But since this is a scroll type of tube, it will have a lot of edges coming on this, out of the surface here. And it may be then either this structure or bamboo-like structure, when periodically closures of nanotube happen when they break off from a catalyst particle. So again, this structure will make very different tubes. One of the reasons is that in a tubes we discussed before, the outer surface will be continuous graphene sheet. Very passive, very difficult to attach any functionalities, any functional groups. In this material, there will be a lot of interrupted layers on the surface. There will be a lot of edges, so you can do a lot of functionalization. For example, attach fluorophores to the surface of carbon nanotubes. Each of those tubes have its own applications, and this is a very, very large family of material. This is great because you can do a lot of different things with those materials. But it is not easy because you need to understand what you need to understand what you deal with, and if you do, you can really obtain properties that you need and produce materials with unique properties. I think it's time for a short break now, and we are going to reconvene in 10 minutes? 11:25. Less than 10 minutes. Yes, please, question.
I think there are 3 factors here.
The issues in carbon nanotubes. And 3 weeks, the entire length of the conference will still probably would not be sufficient for me to cover everything, but I would be able to do a much better job in 3 weeks. Here. But since of course you want to listen about many other exciting topics here, what I suggest you to do, I would like to refer you to some books, including the book that I edited, which has several chapters of carbon nanotubes. But the latest book, absolutely latest, just published, is the 2nd edition of Peter Harris's book on carbon nanotube science. I got it from a publisher with a request to write a review on this book on Friday last week, right before I left for China. So I started to read it on the plane, and this is a good reading to get a big picture about carbon nanotubes. It's very simply written. It covers synthesis, structure, application, all the basics, basically. So this is a good starting point to read here. Also, kind of an interesting observation. I had a long flight from the United States, and I usually pack a lot of papers for review, proposals, magazines that I grabbed in my office after coming from France 3 days ago, and things here. And just in 3 magazines that I read on my way here, one was carbon nanotube device that detects rainbow colors on chromophores, modified carbon nanotubes which are used to make like miniature camera which can recognize in the nanoscale different colors. Another one on cars and SRAs painted pictures, and I heard that you already had a lecture on cars, so you know what this Raman spectroscopy techniques is, right? So carbon nanotubes are really very widely studied for a very, very large number of applications. So depending on what your field is, you select what kind of properties you need and decide what to do with those. And now we're going to talk about electrical conductivity a little bit before, because you already know that some tubes are conducting, some tubes are metallic, but we really did not discuss in detail why, except just mentioning. Oops, I've done something wrong, I guess. That this is due to pi electrons. So before going to conducting films, let me just remind me band structure of graphite, graphene, and carbon nanotubes, which are kind of similar here. You can call graphite metallic conductor, but correctly you should call it a zero band gap semiconductor. Because what you have wealth conduction bands touching at the outskirts of the first brilliant zone, and this is a hexagonal crystal here. And pi electrons provide conductivity. What is important is that in graphene in nanotubes, charge carriers are direct fermions, which can be considered like a massless electrons or charged neutrinos that can move extremely quickly on the surface of a tube or graphene layer, and we'll talk a little bit more about it, given this so-known ballistic conductivity. So you can pump huge currents. You can get very large current densities when you use carbon nanotubes. And this is one of the reasons people are so much interested in application of graphene and graphite in electronics. I won't talk about it today, but the problem is that you go to very, very small devices, try to make them smaller than nanoscale. You will have current-induced diffusion, mobility of atoms in aluminum, in copper, in gold, and any other conductor you can put, not in carbon nanotubes. You can have much, much higher current over extended period of time, even at elevated temperatures, and you will still have very high conductivity, very low resistance, and no degradation of your devices here. So this is important to remember here. And graphite has 2 atoms per unit cells, which lead to 2 conical K and K prime points as shown here, giving you ballistic conductivity, quantum tunneling, and other very useful effects here. And because of this, conductivity of graphite is really not controlled by, unlike other materials, by thickness of the conductor. So it's not like you take, say, aluminum or copper wire, and you know that depending on the wire diameter, you will be able to basically follow in simple Ohm's law, generate more or less heat, get more or less current here. It will be just quantized, going very close to 4 E squares over H, where E is the electron charge, H is Planck constant here. So this is kind of a very interesting, very useful potential property of graphene or carbon nanotubes, metallic tubes here. And what is also interesting, whether you inject electrons or holes, you get this type of a symmetric behavior, which is common for materials with a low concentration of charge carriers, such as carbon or graphites here. So those are all very interesting, very attractive potential properties. Again, why tell potential? I already told you before that we're still learning how to produce metallic tubes, separate them from semiconducting tubes, how to get tubes with the properties we need. And this is actually one of the reasons that graphene attracts so much attention, because when you have a single layer of material, it's often easier to handle this layer. So if you can get the same properties as nanotube have in a single layer of graphite, this may be easier for device manufacturing. And this is what games people are playing now. Very similar to carbon nanotubes. You can get graphene stripes with zigzag or armchair edges with different functionality, and you can control band gap of carbon nanotube, graphene. Instead of changing the diameter of a tube, you can control the band gap by changing width of this graphene stripe so making similar devices. So as you see, there are many parallels in electronic and also optical application between nanotubes and graphene. You can in both cases make transparent conducting films. You can get semiconducting properties for very high electrical conductivity, including ballistic conductivity. And again, you need to learn how to handle them and to decide which one is better for your specific application. Okay, I think I'm pretty much done with this. This is the last slide. I wanted to show you just to compare graphene and carbon nanotubes. So, in both cases, you have high mobility of electrons and holes, more than 10 times higher than in silicon. You can get very high current density, ideal electrostatic behavior, very thin films. The bi-screening length is actually less than 1 nanometer for graphene. That's why you so quickly go to pretty much graphite properties when you get more than one layer of graphene. So only up to 10 layers you see differences in behavior compared to bulk graphite. Definitely it's easier to get large surfaces for graphite, use planar processing things here. However, nanotube have other unique properties because they can add high strengths to applications. They can bend. By bending carbon nanotubes, you can change its conductivity very, very strongly using it as a sensor and modulate the behavior of nanotube here. So there are a lot of these interesting things that can be done. Now, let us look into some of applications of those tubes. And I've been asked to talk about thin conducting films of carbon nanotubes. And I think the idea of it is fairly simple. If you have a material that conducts in a single layer, like single layer tubes or multi-layer tubes or graphene, with this very thin film, you can potentially make it transparent. So you can get a wonderful material which is transparent conductor. And applications for this are numerous. So numerous that I don't want to even start listing them. You can probably, each of you, tell many, many examples here. But the challenge is that these tubes, I think we're starting developing problem with the microphone. Again. Okay, I'll move away from all other electronics. So, what is still important? You all have seen a graphite, piece of graphite, right? You know it's a black reflecting material, which is a conductor. Look on your pencil lead here. And even in a very, very thin film, it is still dark. So the idea is here, how to produce conducting networks, which will have high optical transparency and provide the required conductivity. And this is what I'm going to talk about today. What you see here is an image of a cover of a journal with some of our work published last year. And brightness is not very high. It may be a little bit difficult to see. I see it much better on screen. But you see these small wiggles are carbon nanotubes, which are actually guided in this case by nanofibers to provide a combination conductivity along the fibers, at the same time spacing, which gives better optical transparency. So we will talk about this today in detail. And we already talked about pi electron conductivity in these materials. By the way, nanocarbon is one of a few materials, but I know Japanese scientists even talk about there is like a symposia on pi electron conductors here. When people talk about nanotubes, graphene, and related materials that provide this conductivity here. We already talked about electronic structure, brilliant zone. What is important here? I did not mention to you why some of semiconductor tubes, some of chiral tubes or zigzag tubes are metallic and all, for example, armchair are metallic tubes. It all depends on whether set of wavevectors passes through K point or not. And simple calculation shows that it's always the case for armchair tube, and it's not always the case for zigzag or chiral tubes. So the one which have a difference between Hamada indices n and m divisible by 3, this will be the case with pass through K point, and you will get it metallic, otherwise it will be semiconducting, as you see in this case. For example, 10-0 tube is a semiconducting tube. 10 minus 0 cannot be divided by 3. 9-0 tube will be a metallic tube. It's divisible by 3. So this is a difference. This is basically the physics reason why this rule works here. And you already have seen the differences between the tubes, and I will skip ballistic conductivity. Just one thing to remember. Smaller tubes have a larger band gap if they are semiconducting. Moreover, it's inversely proportional to the tube diameter. What is the reason for this? A simple explanation can be given by this way. You know already that planar graphite is a zero band gap semiconductor, so it is conducting. But as I start bending it, stronger I bend it, stronger it deviates from single layer graphite. So smallest tubes have the largest curvature. You remember, the bond angle becomes close to that of diamond here. So stronger it bends, further you deviate from graphite conductivity, further away from zero you go, and it opens actually potentially great opportunity for tunable devices. So you can have nanotubes that are semiconducting like silicon here with tunable conductivity. But after this brief introduction about properties, I'm going to jump to applications here. Of course, applications listed here are just a small selection from a very, very large number. And from this small selection, I'm going to talk virtually about one solar cells display application and we look for conducting films. But currently, for all these applications, for example, photovoltaics or liquid crystal displays, what many of you are interested in, people use indium tin oxide, ITO. This is state-of-the-art transparent conductor, which is very widely used here. However, it has a large number of problems. Besides price being going up and up over past decade, I think about 10 times increase in price over the last decade happened to indium tin oxide, and limited resources, it has a number of other limitations here. And what people do, they're trying to find alternative here for, first of all, for example, photovoltaics, which has become very, very popular now with attempts to move to green energy production, replace oils, make organic cells for photovoltaic applications. And what you need here, you need a transparent electrode, which will have high transparency, low sheet resistance, appropriate work function, will be smooth, and also mechanically stable and very resistant if you want to put this solar cell outside here. Very similar way we can talk about conducting films for liquid crystal displays. You won't have some requirements, you probably will care less about wear resistance and erosion resistance, because conducting film there won't be exposed to rain, dust, and everything else here, but you will still need these films to be transparent and be sufficiently conducting that you can do liquid crystal switching. Depending on the applications, again, you may have different requirements for conductivity. And if you are in this business, you know what is the conductivity required, for example, for liquid crystal switching or for other applications you're looking for. Moreover, there are many applications where conducting transparent films are needed with very modest conductivity. For example, removing static electricity in the clothes, or say somewhere in manufacturing environment when a single spark can cause a major problem. So the range may depend, and with carbon nanotubes you want to be able to produce a wide range of coatings with controllable structure properties. So this is performance of indium tin oxide. You get fairly high 85 to 95% transmission with these films. And therefore for carbon nanotubes targeted performance is close to that of ITO. But again, as I mentioned, it doesn't necessarily need to be at the same level, because there are many applications where you can live with a lower conductivity or lower transparency, depending on the application here, but still need to have a combination of both. And one of the very first applications for carbon nanotubes was as an additive to polymers, to improve electrical conductivity of polymers. Moreover, today, this is the largest volume application. This is the only application in which tons of nanotubes are used every year. And this is a kind of a low-tech technology, because what you do in this application, you replace what kind of material? What is added nowadays to polymers, rubber? Carbon black. So this is a replacement for carbon black. And if you take multi-walled inexpensive carbon nanotubes, which are used in this ton quantities today, you can get percolation at, you see, several percent less than 10%, while for carbon black you will need probably about 15-20% to get decent conductivity. So this is a replacement of carbon black. However, you can do much better if you go to single-walled tubes. You can get percolation at about 0.5%, or even if you disperse them very, very well, 0.1%. So you can make a polymer conducting with just a 0.1% addition of nanotubes if you distribute and disperse them well. Still, for bulk volume applications, if you take single-wall nanotubes, it is prohibitively expensive, because the cost of this tube currently is at the level of hundreds of dollars per gram. Cost of multi-wall nanotubes is the level of $100 per kilogram, and projected to grow to probably $10–15 per kilogram. So, again, if you're not just academic scientists, but think as engineers or business people, if you want to go and work in industry in the future, you need to balance these things. Well, it's great to have single-wall nanotubes, all metallic tubes, and I can get 5 milligrams of this material after a year of work in the lab. Can I make anything of practical importance? Today, not. And here I have this low-cost multi-wall nanotubes, large quantities, but they're somewhat less conductive, they're thicker, they're darker, so it is more challenging for me to get good transparent coating. How I can handle this? And what you need to do is to think how to design, how to combine them and get them both. So what is done by the community? People use a variety of methods. The simplest one is, of course, spray coating. You disperse nanotubes in solvent, you spray it on the surface, and you get a film. And this film contains nanotube, so eventually it can be conducting if you get enough nanotubes in the surface and disperse them well. You can do it by vacuum filtration. depositing them from a solution on a certain surface. You can do lithography. For example, University of Florida logo is imprinted here, getting a conducting film on the surface for probably electronic applications are considered here. You can also do printing and other techniques here. This is UCLA, stands for University of California at Los Angeles. I will show you quite a few slides from George Gruner's group. He is one of the leading researchers in this field here. So there are different ways people do it, and of course PTMS stamping is probably one of the cheapest ones. They all have their limitations. For example, you cannot stamp coatings on a fabric. So if you want to have a jacket which will be conducting, that you can connect your MP3 player to it directly, or that you can change the color of your dress by applying small electric current to it and making smart textiles, you cannot use this technique. You can need to use something else. You may use deep coatings, you can use many other methods here. So there are different techniques existing. But the bottom line is that by using various techniques, you can produce with single wall nanotubes coating, and this again Gruner's group work here, which will have pretty low sheet resistance and pretty high optical transparency. Of course, what you see here in these plots, as you increase transmittance, basically it's a combination of this. You get higher conductivity, you get lower optical transmittance, and vice versa here. But this is ITO behavior. This is a transmittance in a function of wavelengths for ITO. These are single wall nanotubes to different coatings. And you can see you can get very nice, really transparent, clean coatings, and these are 3 examples of virtually invisible coatings and darker coatings on glass. So this is how a carbon nanotube coating usually looks like when you make it on the surface. Yes?
On the right pictures that you show this ITO, do you know what's the typical thickness of that ITO coatings? Because in general, for display applications, the ITO glass is about 30 ohm per square, with transparency roughly around 95%. So that looks like very low compared to.
It looks somewhat lower. I showed in some picture here. You see, it really varies. I'm not sure. You can probably look up a reference. This is from, I believe, Nanoletters paper by Gruner here. So I'm not sure what was the thickness of the film, but what I'm pretty sure that
because that picture is kind of a distorted, for comparison. In general, for display application, nobody used that. That would be used discarded to the change pin.
The reason is that what Dieter is interested in, he is interested in photovoltaics for solar cells. Okay. And this is an application where people usually sacrifice some of the transparency here. So this is the reason here. So that's why a disclaimer I made in the beginning that depending on applications, while general approach is the same, you want to have a transparent and conducting coating, but balance between those can be changed.
I probably seen this paper before. They were talking about this for display application here, this conducting films. So. And I think it's interesting to know that what the techniques, comparisons in this study. But the paper did not say that.
I don't remember, but they also started a company, Unidim, which commercialized this materials. I know that George has separated from the company by now, but this technology is already commercial, and there is a company in California that produces.
I know that company. The guy is Photovoltaics, the director of the company. CEO of the company. Yeah, but they also suffered quite a bit. I think he presented 2008 SIP symposium. There's also issues with this CMP for replacing IPO. There's a grading of conductivity as a function of the pixel wise.
Fully agree. Look, let me just probably, before I move further, tell you that all that we talk about carbon nanotubes now, in general, this is a new technology. Compared to, say, ITO technology, or compared to liquid crystal display technology, it is much, much younger. And if you talk about graphene, and we'll talk a little bit about it later today, like a groundbreaking paper on graphene appeared in 2004, 5 years ago. Really, research, wide research started a couple of years after that here. So we're talking about technology which are just being developed. And there is a lot of room for improvement. And there are many unresolved issues. But this is exactly where I believe most of you who are PhD students now should focus on. So you know what is potentially possible, but what you need to know. It's not like a problem solved and I'm delivering here and showing you a ready solution which is a perfect and cannot be improved further. This is something that can be improved by a lot. And this is what you need just to understand to go. And I will show you just, probably give you some flavor of how it can be done. But what is important, that already now you can produce sufficiently transparent and conducting films, and you can put them on glass, and you can put, for example, on polymer films. And by the way, this is one of important advantages of carbon nanotubes over ITO, that you can put carbon nanotubes on any properties here. You don't need high temperature deposition. You don't have issues with brittleness or cracking of the films if you have it on a flexible display or if you have it in a fabric for smart clothing or elsewhere here. So these issues don't exist for nanotubes, but you still need to work on getting them more conducting and more transparent here. So how people are trying to solve this problem? But not just mixing nanotubes somehow and making a uniform network, but by designing optimized networks of carbon nanotubes. And this is again UCLA work journal here showing. This is a spread code, but trying to show what we want to have. We want to have it like a freeway network, that if you have an accident one place, there is always a way around, so the current can, or like your car in the freeway, can always reach the end point within a fairly short time. It means getting sufficiently high conductivity here. Or like in the spider web. So what is important? You need to have connections between your carbon nanotubes in this form here. But you don't necessarily need to cover all the surface continuously with carbon tubes, because the price you will pay will be in optical transmittance of your samples here. So this is how you play. You want to have it conducting, transparent, flexible, inert, low weight, porous potentially for some applications, and with tunable properties on any substrate. And important for nanotubes, you can do it by room temperature or slightly elevated temperature fabrication. So it's applicable to any surface. This is one of very important applications of carbon nanotubes, unlike ITO here. So let me show. I think I'm already like 10 minutes longer than schedule allowed here. And Ivan, what do you want me to do? How tight are we on the schedule here? Should I
spend like 10 more minutes?
10 more minutes here. Okay, so what I'm going to do, I'll go till 12:30, and after that I will stop, and then we will continue talking about tomorrow, and then we move to Raman spectroscopy for the second lecture tomorrow. Fine. So I want to show you some of the work that we have been doing in our laboratory in this area, developing the films here, in which we suggested two make this type of a spider web by a different method as I showed you in the beginning. What we do, instead of putting carbon nanotubes by spraying, deep coating or other methods, everyone on the surface, we want to guide them by using polymer fibers. How many of you are familiar with electrospinning? Can you raise your hands? I see 2 hands raised. Again, not really a forest of hands. Let me tell you a few words about this technique. This is a very common method now for making nanofibers. Very, very thin fibers, sub-micrometer in diameters, going down to 20, 50 nanometers. The idea is very simple. It was patented long time ago, 1934, but really became a common technique this century, in the last decade. What you do, you take a solution or melt of polymer, put it in syringe, and apply high voltage, 10 to 30 kilovolt. So, solution of the material or melt is drawn out of the syringe by electrostatic field. It must have at least some conductivity, and it breaks apart because of an instability of the droplets of the solution here, forming very, very thin fibers if you have a viscous polymer solution inside. So this technique is used to make very thin fibers for filtration applications, for smart textiles, for many, many other applications. And this is a way to make really very thin fibers. And several years ago we showed that it's possible to etch carbon nanotubes to polymers, and nanotubes will be larger, nicely drawn along the fibers. And in this paper in 2003, in Advanced Materials, which has been cited more than 200 times by now, I believe here, we announced that we will make very nice, very conducting nanofibers, polymer nanofibers. However, when we did measurement of conductivity later, we were disappointed. Because what happens? Nanotubes align inside the fiber, along the fiber axis, very nicely aligned. So there are very few contacts between the nanotubes. Moreover, with polymer on the surface, they are pretty much insulated. So you get nice fibers, nicely distributed, but you cannot really benefit much from conducting nanotubes inside here. So what we decided to do later, we decided to use these fibers as guides for nanotubes, putting nanotubes not inside, but on the surface of these fibers. So what we did for this, we took multiple nanotubes initially. We have done later this work on single-wall, double-wall tubes, but the goal initially was to make coatings where we can use multiple nanotubes, because multiple nanotubes you really cannot make a continuous coat. It won't be transparent. It will absorb at least 30% of visible light if you make a conductive films here. So we took multiple tubes. You see these films are commercial. They come in large quantities from Arkema with about 10-20 nanometer in diameter. We oxidize the surface to give some negative charge to these nanotubes. So the formed solution, which is stable, but you see it is very dark solution in DMF of nanotubes, so you cannot have a thick film. And this is nanotube paper, just filter it after dispersion things here. But when you have this negatively charged carbon nanotubes, and if you take a positively charged polymer, you can assemble carbon nanotubes on the surface of polymer fibers by simply electrostatic assembly. So what we do, we have oxidized tubes with defects and COH groups on the surface, and assemble them on fibers. For example, in this case, it's a polyamide 11. It can be pen fiber. It can be many other fibers that have some, for example, amino groups or other positively charged functional groups. So what will happen afterwards? These nanotubes will stick to the outer surface of the fiber. This is a scanning electron microscope image when you have a 100 nanometer fiber and probably 20 nanometer in average nanotubes on the surface. It's colored to make it easier for you to see. And you see nanotubes assemble very nicely along the fiber. And if you take a positively charged polymer, you can assemble on the surface. But all of them are exposed, all of them are interconnected and cross with each other. And this approach is very simple. So what you do, you produce a fabric, you can kind of dip it in this dark solution that I showed you in previous slides, like this one, and this solution will become immediately transparent because all nanotubes will be drawn to the surface of the fiber within less than a minute. Here. So, this is how it is happening. You get nanotubes on the surface of the fiber, and you get a conducting fiber network. Initially, we used very similar approach to produce not the fibers, but make coatings for dissipation of charges, and I hope my movie will work. And I don't think it is going to work. Well, forget about the movie here, but you will have to believe me that you can remove static electricity by this technique. So, what do you get in case of the fibers? This is just a black and white version of an image that I showed in the beginning of the cover for journal. Now, instead of having a continuous coating of nanotubes covering of the surface, you get fibers and carbon nanotubes. These thinner lines are tubes like small wiggles, and thicker ones are 100 to 200 nanometer polymer coatings here. You have this pattern with larger open spaces which improve transparency. And this was the idea of this design, to have multiple nanotubes which, when they are in contact with each other, provide conductivity at the same time by using this design improve optical transparency here. Now, what do we get here? Depending on the laser spinning time and thickness of the film, you get, of course, resistance decreasing if you have more material, but you also have transmittance decreasing. However, you may still get transmittance pretty close to 90% when you have thin, ideally virtually monolayer of the fiber coating on the surface. However, the transmittance initially is fairly low, and let me show you, oops, I don't have a picture why, but let me explain why it is initially low and will drop significantly. Because when you have fibers like that, you have a kind of a whitish coating because you have simply light scattering on a network of fiber with gaps, as you see, very close to wavelengths of visible light, like half a micron between the fibers. So what you can do, you can heat this polymer, that the fibers melt and stick to the surface. And what you will have, carbon nanotube network will still follow the trail, stay exactly where the fiber was, but forming a continuous network with decent values of conductivity here. Still, when you look at different type of nanotubes used, you will see that multiple carbon nanotubes will have, of course, the highest sheet resistance. After annealing, it drops significantly, and melting tubes here. But if you use double wall carbon nanotubes, you can get very close to 100% transmission, and at the same time have relatively decent sheet resistance here, which doesn't reach that of single wall carbon nanotubes or ITO, but comes a bit closer. So, and I think our conference chair gives me a sign that I should probably stop at that point here. If there are any questions right now, I will take them, and I suggest we'll just continue talking about these materials and conducting transparent films tomorrow. Any questions at that point?
Is it possible to control the length of the carbon nanofibers?
Polymer nanofibers.
Carbon nanotubes.
For carbon nanotubes, yes and no. Potentially, yes. You know, people are still dreaming about making a space elevator, which will require continuous carbon nanotubes with the length of thousands of kilometers here. Currently, people are capable of grow like 1 centimeter carbon nanotubes. Most tubes which are used for practical purposes have lengths of tens, maybe 100 of micrometers.
And is it possible to fill the gaps of the multi-walled carbon tube by other nano materials?
Yes, it is possible. We even work on filling carbon nanotubes cylinders with some material. It depends on the application. In many cases, people fill those with some nanoparticles. For example, silicon or tin nanoparticles are used inside for lithium battery applications. We use gold nanoparticles to do surface-enhanced Raman spectroscopy. I will be talking about it tomorrow. You can also fill with other materials, but if you, for example, try to fill the cavity in carbon nanotube with other metal as a conductor, you really won't help much in conductivity, because largely the surface layer of carbon nanotube, the carbon shell, is responsible for the conductivity you get. Yes,
because the carbon nanotube itself is anisotropic. Is it possible to use carbon nanotube from any liquid crystalline phases?
Yes. First, if you disperse liquid crystal in a solution, carbon nanotube in solution, carbon nanotubes behave like liquid crystal. For example, first experiment went done on highly concentrated solution of nanotube in sulfuric acid oleum, showing that this dispersion saw liquid crystalline behavior. There is no practical application, to the best of my knowledge, for this type of a dispersion of carbon nanotubes in sulfuric acid, but the behavior is there. On the other hand, I will show you some slides tomorrow if I can find them on my computer. People use carbon nanotubes to improve switching of liquid crystals, and there are attempts to pretty much modify the property of liquid crystal materials by adding carbon nanotubes to those. Well, I suggest you just keep your question for tomorrow, and I will be glad to take more questions.